Hello, everyone, and thank you very much for coming tonight. Can everybody hear me okay? Seems like yes. All right. So I want to talk about star formation in this talk, and I'll start by giving you an idea about what you see when you look up at the night sky, especially in a rich environment like this in the center of the Milky Way. So you might see various different features. You see these countless stars throughout the entire field, basically everywhere you can see here. You might also see these areas of hot gas. These are material around newly formed young stars, and some of these are visible through the telescopes tonight, although we probably won't see them because they're a little bit overwhelming in Toronto's light pollution. We would also see some of this cold gas and dust. And this is pretty hard to see, but if you're in a dark site, you might see that there's a bit of a dark area in the center of the Milky Way, and that's exactly what this is. But what's important for this talk is that all of the stuff that you see here relates to both, how you produce stars and how you produce stars affects what you see in the night sky. So, I need to, there we go. So how does star formation take place? So it starts in a dense cloud of gas or dust, similar to those dark clouds that you just saw on the previous image. And as that cloud of gas and dust is acted on by gravity, it collapses. As it gets denser, it starts to fragment and produce these little clumps within. And each one of those clumps has the ability to form a star. And then eventually, once you get to the point where you have a new protostar forming in the center of one of those clumps, you get like a disk around it. That disk can form planets, and eventually you get something like the solar system. But you can imagine that almost everything happening here can affect something about the universe that we see around us. So if we have more fragmentation of gas in these small cores, that might mean that we get like more binary stars. If we have a denser environment where there are more stars interacting, you might have some disruption of the disk, which might mean that it's harder to produce large solar systems like the one that we have, where we have, Neptune and Uranus way out far in the system. So in order to understand how we got here, we need to understand the process of star formation. So how do we get stars to form in the first place out of these clouds? And the answer to that question is not necessarily as trivial as you might think. You might think, cloud of gas, gravity makes things collapse. Boom, we got a star. Not necessarily that simple, because we have all these stars everywhere in the universe, and these stars are emitting a lot of energy in the form of photons, and that energy is making the particles in the gas go really fast, so fast that gravity is not able to hold on to them and bring them together to form a star unless you have certain conditions. And things that could cause those conditions could be things like, a collision between two clouds, cloud A colliding into cloud B. As they collide, you get compression that allows star formation to begin. You might have stellar feedback. This is when young, massive stars emit so much light, so many photons, that it actually pushes on the gas and produces compression as it pushes on that gas. Supernovae have the exact same effect to that. And then we also have things like galactic dynamics. As the galaxy itself work to conspire to produce these overdensities that can allow star formation to take place. A lot of this is currently unknown. So I'm going to start by showing a few examples of star formation in relatively massive environments. And what you probably notice here is that you see a bit of a pattern where you often have some of the brightest stars located in the center. And in the case of this one, the center is a little bit off screen. But you see a lot of these brightest stars located in the center of the region. And then towards the edges, towards the shells, you get this sort of like these overdensities around a lower density center. And what that's caused by is a massive amount of radiation coming out from the central cluster, pushing on the surrounding gas and producing this cavity where we have these overdense regions along the edges. So in the Orion Nebula, there's the central cluster, there's the area around it. I'll talk more about this in a second. And then the pillars of creation, which you've seen these like many amazing images of, that is the edge of a bubble driven by the cluster that is up here. So just having a closer look at the Tarantula Nebula here, you can see a lot of these features very clearly. So we get that central cluster in the middle. Then around that central cluster, we have a shell. We actually have multiple shells in this case. We got one here, we got one here, we got one here. There's sort of like overlapping shells produced by different stars. And in the center here, the reason why there's such a big shell here is because the most massive star known to us is actually in the center of this cluster. Then around the edges, we have these ridges. And these ridges are where gas is piling up due to the feedback from that central cluster. And then you also have, around all of this, you have a bunch of unprocessed gas to the upper left there. So you can sort of imagine, a bit of a sequence here where we can have multiple generations of star formation beginning here, then progressing to here, and then eventually it's going to use up this gas as that shell expands. So that sort of sequence is what's called sequential star formation. And triggered star formation is just the process of a generation of star formation being triggered by the previous generation. And you can see a lot of the same processes that you see in the Tarantula Nebula in places like, at much larger galactic scales. So this is the galaxy Messier 74, and you can see a lot of incredible features here. You see these large spiral overdensities weaving throughout the galaxy, but you also see bubbles all over the place. There's a big one here, a couple here, one over there, one over there. So we got bubbles throughout this entire region. And these are all produced by the same processes that you see in the Tarantula Nebula, by feedback from massive stars. And you can see that when you have interactions between these spiral overdensities and these bubbles, you often get events of star formation. So for example, we have a couple of young nebulae that are produced by young stars right here, there's a little bit there. So we seem to have this sort of interaction between these large-scale processes driven by the structure of the galaxy and the interaction of that with these smaller-scale bubbles. And you can just see the incredible diversity of these features from this gallery from the JWST FANG survey, where you can see things ranging from those galaxies with very strong spiral structure, like M74, which is repeated here. But you can also see, another case like that is NGC 4254 with this really, really nice spiral, but a ton of bubbles embedded in that spiral. Then you also get cases like IC 5332, where rather than having very strong spiral structure, it's much more of what you would consider to be flocculent. That is, rather than having a bunch of distinct spiral arms, you get a lot more of a knotty structure. You get like a whole bunch of knots of gas that exist within this larger pattern. And it's often not simple to place the Milky Way, and especially our environment around the sun, in this diagram. And you can see the massive diversity in these galaxies. So understanding where we exist in this gallery is really important to understand what sort of star formation is happening near us. Oops. I shouldn't have done that. All right. So one other thing that's really helped our study of star formation lately, aside from looking at these structures in other galaxies, is looking at these simulations. So much of the physics of star formation is known. So we know that gravity is important. We know that fluid dynamics are important. That is the physics of fluids. Gas is a fluid. So that's important to understand how this gas evolves. We also have magnetic fields, which are often neglected in many fields of astronomy, but it's important not to neglect them in the case of star formation. And then we also have, as I mentioned before, feedback from young stars that can push on the surrounding gas. So in the case of this simulation here, we start with a dense cloud. That cloud starts collapsing. You can see the formation of these little fragments in that gas. Then eventually you start getting stars forming out of that gas, and those stars cast away the surrounding medium, leaving behind a star cluster or a stellar association, depending on whether or not the stars are gravitationally bound to each other. And then eventually the gas gets completely cleared. So the advantage of simulations is it lets us compare real structures that we can see up in the night sky to these simulations, and we know exactly how these simulations evolve because we have the entire time scale on them. So this can be a great bit of context to understand what we're seeing when we're looking up at the night sky. And now I'm just going to play this simulation here. So this is a really amazing simulation from the same suite as in the previous slide from the StarForge collaboration. And I'll just let this play here for a little while. So what you're going to start to see is that within this cloud of gas, you're going to get some overdensities. And those are indicated by the lighter, whiter regions here. And when you start seeing stars form, you're going to see little white dots. I think that's some of the first stars right here. Now, one thing that you'll see a lot of very soon is these little jet-like things. Those are called outflows. And what those are is that when you have stars actively forming, you get a lot of accretion of gas in a disk onto the surface of the star. And when magnetic fields act on that, it actually ejects a lot of that gas perpendicular to the disk, producing these long outflows. And you're going to see a ton of those in a second here. But you have some newly formed stars here. You got a couple outflows going off there. Actually, let me turn off remove that. That should help a little bit. So yeah, we got a bunch of outflows happening. We got multiple locations where star formation is actively occurring in this simulation. And what you're going to see eventually is that all these stars are going to start to assemble into a larger cluster. So you're getting this collapse towards a central open cluster. And you see that we have like a lot of outflows going off now. We got all these crazy outflows all over the place. And these are all great indicators that star formation is actively happening. You also see some of these bubbles start to form. So these are two massive stars emitting a lot of radiation. And you can see that there's already a cavity forming around them. But you're going to get a much larger cavity in a second here once all of the stars in this cluster end up collapsing towards the center and producing this really incredible large bubble structure. So we're about to get that now. We have a ton of these outflows occurring in the center here, and we're going to start getting a lot of clearing from a bubble. You're starting to get that now, where you have this massive flow of material. Yeah, there we go. A massive flow of material producing that central bubble. And I'm just going to quickly move it ahead a little bit here so you can see sort of the end of this. And what you see now is that you have a big cavity in the center. And then around the edges, you can see that star formation is still happening. And that's indicated by those outflows, which again only happen in locations where star formation is actively occurring. So we get this pattern of, you build a central cluster, you clear the center, and then along the edges, you get these areas where star formation is actively happening. And there is the first supernova going off in the region, injecting more energy into the surrounding medium. So that's the sort of result that we have in these simulations so far. And you can see this incredible diversity of processes, this incredible complexity that leads to these star formation events. And there have been some other scenarios aside from just like a spherical cloud that have been tested here. And one example is these cloud-cloud collisions. And this is where you have cloud A and cloud B. In the top row, these two clouds are moving towards each other. In the bottom row, they are just staying where they are, not moving. And you can see that in the top row, you get a much denser region in this gas. And that denser region produces a lot more stars compared to the bottom frame where almost no stars get produced. So that is to say that the existence of a collision can be instrumental in causing star formation to occur. And going on to much larger scales here, we can see that these simulations can also demonstrate the evolution of an entire galaxy. So this is from the Fire suite made by Viviana Asaguera here. And what you can see is, again, that interplay of these bubbles with those spiral structures. So you can see large spiral over densities in this gas. And then you can also see that there's a lot of bubbles here as well. And what I want you to bring your attention to is these red particles here. And these red particles they're material that eventually ends up in a sort of ridge of gas right there. And that ridge is similar to an overdensity that we see in the solar neighborhood, where a lot of nearby star formation is occurring, called the Radcliffe wave, which I'll discuss quite a bit later on. But what's important to note here is that even 50 million years before the present, at the start of this simulation, that gas is spread over several of what we would consider to be spiral arms. And it's only after star formation occurs right here that you get a bubble expanding. And that bubble is what sweeps up that ridge of gas and produces that overdensity within the gas that can form all of these stars. So, we've got this incredible interplay of these spiral overdensities and these bubbles. So what's interesting to us is which of these processes are dominant in our local environment and which of these processes guide star formation in our own Milky Way galaxy. So let's have a look at the Milky Way galaxy and see what we can learn about that. So this is the typical conception of the Milky Way that we've seen. And this is an artist's conception. The reason that it's an artist's conception is that we are inside of our own galaxy. And it's very hard to take a picture of something when you're inside of it. And that becomes really clear when you look at the Milky Way from the Earth, where we're basically looking at it on the edge, looking towards the center here. This is the center of the galaxy right there. And you can see that there are basically layers upon layers of all this dark stuff, and that's all the dust. And dust is where star formation is happening, so it's really important to us. But if there's, 4 layers of dust between you and the thing that you want to learn about, that's going to be pretty difficult, right? It's going to be pretty hard to see through all that material. So if you want to understand the structure of the galaxy, it's important to figure out how you're going to, identify where all this dust is in spatial coordinates and what that can tell us about the structure of the galaxy. The one thing that we can do first is we can look at where star formation is actively occurring to get a sense of what star formation looks like nearby. So we can see this incredible variety in these shapes in these star forming regions. And that goes from cases like the Orion Nebula, where we have this massive star formation, a lot of very hot blue stars in the center here, and then this sort of like bubble-like structure around it. We also have things like the Taurus molecular cloud, which is down at the left side here, and you can see that this is sort of like a bundle of these little filaments. And each of these filaments has an overdensity along the center of it that can begin to form stars. We also have cases like the Cocoon Nebula, and this is a case where we have these filaments that will eventually form stars over here. We've got active star formation here, and in other cases like the Cocoon Nebula, we also have older generations going off further in this direction. So you can sort of imagine a progression from old star formation to current star formation to future star formation. You also have cases like the Rho-Yuhi complex, and this is one that I currently have a student working on because it's such a complex and chaotic environment. But this is a set of filaments that's surrounded by other young stars that are producing feedback, that are acting on this gas. You can see sort of streamers going off of some of this gas. This is gas that's been blown by some of the nearby star-forming regions. So you see a lot of interesting features here, and some of this hints to how those star-forming events took place. For example, those streamers that I just mentioned. But this picture is very incomplete in that most gas in the solar neighborhood is not star-forming. So if we want to get a full concept of the full-on dynamics of the solar neighborhood, we need to look at the other gas aside from what is actively star-forming. And we can do this using what's called dust mapping. So when light from stars passes through dust, it gets redder. And this is exactly the same concept behind why the moon looked really orange a few days ago. In that you have all of this, all these particles from the forest fires that are getting in the way of the moon, and they're taking away the blue light and leaving behind more of a red image there. And the same thing happens out in space. Whereas if you have a star with no gas between you and the cloud, we can see that it's nice and yellow. It is its intrinsic color. Then as you look through a large amount of this dust, you see that the light from that star ends up getting much, much, much redder. And if we have the locations of a ton of different stars along many different sight lines with many different distances, we can reconstruct exactly what gas is where. And this allows us to produce things like this map from Gordon Edenhofer. This is in the nearest 1.25 parsecs, which is about 4,000 light years, if I'm not mistaken. And you can see a lot of interesting structure here. So, for example, we have the Radcliffe wave, which is that long linear structure that I mentioned a while back, where we have this long ridge of relatively high density dust and gas, and that's also where a lot of recent star formation has taken place. You also see the split, which is this sort of shorter structure consisting of some really dense clouds, including the chameleon clouds, serpens, the Aquila Rift, etc. And you can sort of imagine if you arrange all these, that they might sort of conspire to form sort of arm structures. So that is, these overdensities might follow spiral arms that continue on into the galaxy. However, you can also look at this in the opposite direction, which is, well, what if it's just governed by bubbles? What if all that we're seeing here is just bubbles, and we're just seeing bubbles all the way down? And honestly, when you look at this, it sort of looks sort of convincing, doesn't it? So we have, a big bubble here, maybe a couple of bubbles here, big bubble there. This one's very well studied. We know that that's a real convincing bubble. We've got maybe a few bubbles over here. So it's not entirely clear just from looking at these images, what we're seeing is dictated by the spiral structure, and what that we're seeing is dictated by these sort of gas and dust processes, like this feedback from these young star-forming regions. And there has been some work done to try to like marry the concept of these spiral overdensities to these bubbles. And in the case here, we see that in the solar neighborhood, we have what's called the local bubble. And that local bubble, a lot of its star formation is occurring on the edges, specifically the edges that exist towards the split and the Radcliffe wave. So that might mean that we have interaction between these two structures that is driving the star formation in these locations. But it's unclear how much of that is just luck of where there was gas to bunch up, and how much of it is actually a spiral structure interacting with these bubbles. So what do we have so far? So first of all, we have examples of many local star forming regions. So we have a good idea about what star formation looks like locally and what sort of processes are important in the solar neighborhood. We also have examples of galactic scale gas and dust patterns, like these shown in the FANG survey, where we see these incredible spiral galaxies with these bubbles, these spiral arms, that all interact to allow star formation to occur. We also get information on local dust patterns, which sort of gets us a local snapshot of what dust looks like in the solar neighborhood and how that might compare to these larger images from things like the FANG survey. Then we also have simulations of star formation on various scales that show us how star formation is expected to occur given our known physics on both local and on galactic scales. But what do we lack at this point? Well, the first thing we lack is time resolution on real star formation events. So, when we look at these faraway galaxies, when we look at our nearby star forming regions and take pictures of them, we get all this incredible detail on, where the stars, where the gas is, maybe how it's moving if you use the right methodologies. But you don't have any information about what happened in the past and how that might lead to what you're seeing in the present day. So that's an important thing to get information on. You also lack clarity on the local forces driving star formation. You have all these things that look like bubbles, that look like these spiral structures, but it's hard to determine which of these processes dominate locally. We also have these great simulations, but a lot of the models don't necessarily work, especially locally, with really physical environments. Going back to that image of the local gas and dust, you see a lot of these overdensities. They don't look very spherical, do they? And that big video simulation that I showed you before is just a spherical cloud collapsing. So if we're imagining that everything is spherical, we're probably going to be missing some patterns that allow certain star formation processes to occur. And I'll discuss more of what I mean by that later on. But what we do to address some of these questions is what I like to call stellar paleontology. And there's actually something else called stellar paleontology, but I think my metaphor is better, so I'm going to go with that. So how does stellar paleontology work? So it works on the fact that when stars are really young, they don't actually start out in their final state. So that is, the sun has been practically the same for about 4.5 billion years, just burning hydrogen into helium in what we like to call the main sequence. But within the first, 100-ish million years of star formation, the stars actually aren't in their final state. They're bigger, they're bloated because things are collapsing from a cloud. The star actually forms before it's done collapsing. So we can detect that stars that are younger are actually brighter. So on this diagram, brighter is up, hotter is to the left, and you can see that we have this sequence of stars becoming dimmer and maybe a little bit more blue over time. So we go from something like this down to something like this. And this change in brightness, this change in luminosity, can be detected with this incredible spacecraft called Gaia. And Gaia has been doing just incredible work. It's been just scanning the sky constantly for the last decade. It just finished up its science mission earlier this year. And you can see that it observes the positions and the luminosities for nearly 2 billion stars. And in doing so, when it repeats observations of the same area, it can determine where a star moved over that time. And that can give you information on where the stars are, their luminosity, and also how they are moving. And how they are moving is absolutely critical to reconstructing the story of nearby star formation. And remember, those luminosities from before, those can give us information about the ages of the stars. So if we have positions, we have velocities, and we have ages, we can trace the stars back in time and reconstruct how star formation has occurred in the past. So looking at the data from Gaia, we can see this, we can see that there's a large region in what we call the Premian sequence where we can reliably identify stars as being young based on them being overluminous. So same as the last diagram, brighter is up, hotter is to the left. Then we have this big region right here where we can reliably produce or identify stars as being young. And this gives us a fossil record that covers roughly 50 million years of star formation in the solar neighborhood. And let's focus in on a little region of this, this diagram here. Let's rotate it, and let's compare it to the fossil record that we see in our own Earth. So, as we go down into like deeper and deeper layers of rock on the Earth, we see that we go from, mammoths down to, stegosauruses, down to like early amphibians, right? As you go further and further down, the older and older the animals get. Well, same idea in stellar paleontology. The further you go down on the Premian sequence, the older the stars get. So at the very, very top of this diagram, we have something like the Orion Nebula, which has been forming stars for about the last 2 million years. And this corresponds roughly to the time scale on which our early human ancestors like Homo erectus were on the planet. Going back further to about 5 million years, we have a population that's going to get really important in a few minutes here. But it started forming around the time that terror birds were apex predators on the plains of North America. Going back to when Sco-Sen, the largest of the major star-forming regions in the solar neighborhood, started forming. That was roughly when the first seals started swimming around in the oceans. To the Austral complex, this is the nearest of the large groupings of stars. This thing started forming around the time that there was a crazy murderous hippo relative that ruled the Earth. I didn't know about that until I searched some animals for this. And then going further back, we have Alpha Persei, which is really at the limits of what we can see here with this method. And at about 70 million years old, that corresponds to when the T-Rex was still kicking around. So we got this nice record of stars that corresponds to roughly, 70-ish million years, depending on how generous you want to be about our capabilities here. And this produces a record that we can use to learn about the previous evolution of these star-forming regions. So one of these regions is the Circinus molecular cloud. And this was brought to my attention by my collaborators Travis Rector and Lisa Prado. And they basically took these incredible images from the DECAM instrument in Chile and found that these two regions have very different shapes compared to each other, despite the fact that they sort of like, share the same larger cloud. In the east, we have this very dense, sort of blobby structure to the cloud. And in the west, we have this much more filamentary, much more delicate sort of structure. So why do we have such different morphologies in these two regions? Well, we can consult the fossil record to learn about that. And what we do when we look at that fossil record is we find that there is a terror bird lurking in the upper left of Circinus East here. So this is what the distribution of stars looks like when I look at it in this lens of the fossil record. So this is just a map of where the stars are on the sky, and I've colored them by what grouping of stars they reside in. And then if you take those images from before and place them over top of this map, you see that these images are just a tiny component of a much larger complex, and that much larger complex has been forming for about the last 5 to 6 million years. And in the center here, around what we call the Circinus Central region, Circe, we have 5 or more stars with 10 or more solar masses. And stars like this emit a massive amount of radiation and produce a massive amount of force on the surrounding gas. It has the ability to really impact how star formation evolves around them. So what else can we learn about Circinus from this record? Well, one thing that we can notice is that there are a couple of patterns, both in age and in velocity. So both of these are just, along some axis, how does the age vary? So in both cases, we have some central cluster right here where we have old ages, then it gets younger, which is this darker color, younger, younger, and younger, going in these 3 different directions. Same idea on sky. We have younger, and we have younger going out from that central cluster. And when we look at how the velocities change with distance from the central cluster, we have low velocities in the central cluster. As we go out, we get we get faster and faster velocities relative to that central cluster. And that pattern actually replicates something we see in one of these simulations that I mentioned earlier. This is from that AstroTours simulation. And you can see exactly the same patterns here. So that is, you have old in the center, and then as you go out from that central population, we get younger and younger stars, younger and younger, and then younger. And then as you look at the distribution in velocity space, so this is distance, this is velocity, as we go further from the center here, so this is the center, we get higher velocities, and we also get darker colors, which means younger ages. So exactly the same pattern. The further we go from the center of this population, the faster the velocities and the younger the ages. So what we can do to learn about how star formation might have occurred in Circinus is we can look at the simulation that produced this result and use it as an analog to understand what we're seeing in Circinus. And this is what that simulation in the StarForge suite of simulations looks like. So you see that you start having a bunch of little clumps of gas that start forming stars. Those stars end up collapsing towards the center, and you're going to start getting a shell around the central region, the same as in that large video that I showed you earlier on. And surrounding this, you start getting star formation in these little clumps. And what I want you to keep an eye on the next time I let this play is that over time, you actually see star formation propagating up these residual filaments. So let this play through again. So we have initially the collapse of this cloud, the assembly of a central cluster. So we just have stars beginning to fall in towards the center right now. And then right after it forms its central cluster, you want to get a shell forming around the center. And you're going to get star formation around that shell. And that's indicated by these other colors here. So your blacks and your greens and all that. We get star formation here, here, and here. And then over time, you see that star formation propagates farther and farther out along these filaments. Then same thing here. We'll get another generation after these two up there, like that. So we have this pattern of star formation propagating up these filaments, and it produces both the age gradient and the velocity gradient that we see in Circinus. So this produces a nice model for how star formation may have taken place in this complex. And that is that the sequences that we see emerge from formation in a shell that is being blown away by the central cluster. And the differences in velocity are produced by differences in exposure to the feedback from the central stars on the gas around the cluster in that shell. Whereas stars that are, or gas that's immediately exposed to the bubble, that compresses the gas there almost immediately, and it forms stars before anything can accelerate all that much. Whereas further out, you get a much more gentle acceleration, which lets the gas move much, much faster before it becomes dense enough to form stars. That produces this gradient in both velocity and in age. And we can actually see the evidence for there being this feedback-driven shell around Circinus in the clouds that I mentioned from before. And that is that when we look at Circinus East here, we see that there's actually two components of the velocity in Circinus East. In the center of this cloud, we have velocities that are practically zero relative to the central cluster. And then as we go further up, this is closer to the central cluster in Circe, we see much higher velocities. And these velocities are almost identical to what we would expect from gas ejected from the central cluster. It matches almost perfectly with other populations that we see at that same distance from the central cluster. So that is to indicate that we have stationary gas, we have ejected gas, and these are now colliding. And during that collision, we are seeing the bunching of material forcing the gas in Circinus East into this dense morphology, whereas in the West, we have essentially nothing acting on it. In fact, it's partially shielded from the central cluster by Circinus East. And this is producing this environment where gravity can just do as it pleases, and gravity tends to like to produce these nice filamentary structures in the absence of any major velocity differences across it. So, are the patterns that we are suggesting in Circinus universal? I would say almost certainly not. So Starforge, as I mentioned before, only takes just a cloud of gas, lets it collapse, spherical cloud, lets it collapse, and see what sort of star formation you produce. And what this ends up doing is it focuses a lot of the collapse of the cloud in the center, which means there isn't a lot of gas left over after the central cluster forms to produce later generations. But out in space, you're likely to have like large clouds surrounding these spherical areas that are collapsing, and this could produce residual gas that can drive many later generations of star formation. And because of that, we haven't replicated either massive later generations, so this is later generations in the shell that are similar in mass to the first generation, and we also haven't generated these sort of like 20 plus million year star formation histories like we see in SCO-SEN, that seal, that thing that started forming along the time that seals were swimming around, where we have 25 million years roughly in the center here, going out to 0, 0, and about 9 million years in these three different directions. And there's been a proposal for how star formation might have happened in SCO-SEN, and it involves having a first cluster that forms, and then you have a cloud of gas near it, and that cloud of gas gets continuously accelerated by the central cluster. So you get supernovae, you get feedback, and they push on the gas there, and that produces stars on the edge that is closest to the central cluster, but then it actually pushes the gas clear of the stars. So you get this trail of gas being pushed away more and more and more, and then the stars being left behind as that gas gets accelerated. So this produces this effect of, you start with the cloud, that cloud gets pushed away, and you get this trail of stars with increasingly young ages and increasingly fast velocities going away from the center. But there have not been simulations to test whether this is plausible on the timescales that are suggested here, so we're still waiting to be able to do simulations like that to really understand whether this is possible. And we actually have a test lined up to do exactly this. So, around Cercinus, the same population that I just discussed here, we actually have large amounts of unprocessed gas that remains around the central cluster here. So we have Cercinus east and west here, and then we also have this large northern cloud that is massive and contains a ton of gas. So, the concept here is that, if we know how the gas is moving in this large complex, we might be able to understand how it will evolve in the future. And in fact, I have a collaborator at McMaster that does exactly this. That is, take observations of gas from radio telescopes and put that into a simulation and use that simulation to understand how it will evolve in the future. So because of that, we have recently submitted a proposal to do some observing with this telescope here in Chile, starting with Cercinus East, but eventually moving it to focus on the entire complex to try to do the simulation and to try to understand whether the model presented in the previous slide by Laura Posch actually is plausible. So where do we hope to go from here? So eventually what we want to do is we want to reveal all of these bubbles, these spiral arm aligned structures, and any other features that dictate how star formation has occurred in the last 50 to 100 million years. And by doing this, what we can do is we can reconstruct the conditions of star formation in various different environments in our galaxy, and what sort of effects might have been present when something like a binary star forms or a planet forms. And if we have information about the formative dynamics of many different planets, that can eventually get us to the point where we can infer, based on what we see in our own solar system, what sort of star forming region likely led to the solar system and the planet that we live on. And some work has already been done to try to understand the structures that have led to star formation locally. So this is work by Cameron Swigum in Vienna. And what happens is that when you take all of these clusters in the solar neighborhood and you trace their velocities back in time, you end up getting that about between 20 and 45 million years ago, you get these compact configurations like these. And over time, they eventually drift apart to produce what we see in the present day. But especially in the case of the Colander 135 group right here, we actually see old stars in the center and then increasingly young stars going out, exactly the pattern that we would expect in this sort of bubble-driven scenario. In cases like Alpha Persei and the M6 family here, that pattern is a little bit more muddy. And as a result, this might be not just a single bubble, but rather a fragment of a spiral arm, for example, producing this distribution of stars. But this is all to say that we're starting to get a sense of what these structures might have been that have driven local star formation. And I took my own stab at this. This is something that I whipped up in like an hour or so. But basically, this is just, take where the stars currently are, or you trace them back in time, and then you let them play forward and see where they ended up in the past. And we end up getting, now don't put too much weight in this because I, again, whipped it up in an hour. But what you see is that some of these groupings of stars end up coming together right around the time that we know that that star formation occurred in those regions, right here, and right here, and right here. And then after that star formation occurs, they drift apart to where they are in the present day. So we get the same structure of large amounts of star formation happening together and then drifting apart. So last thing that we want to do here is discuss planets. And this is something that can give us a lot of information about how planets form by looking at the sort of planets we get in different environments in the solar neighborhood. And there's already been some work done on this. So for example, Beta Pictoris, there's already this famous image of this little Saturn mass planet embedded in the disk of Beta Pictoris. And that's the best known one. But we also have more planets that have been discovered in the Cepheus Hercules region. And this is a project that I was involved in. This is we got sort of lucky here, and that the field that the Kepler spacecraft was staring at for many, many years just happens to align with where there are stars in this star-forming region. And there just happened to be 4 planets that were in that region, and 3 of those were the 3 smallest ever discovered in this age range. So we're already getting some new planets that are the youngest ever known in these environments that can give us a lot of information about how star formation progresses by getting more of these and by producing this map of how that evolution takes place in the early formation of these planetary systems. But of course, we need a lot more statistics to be able to say anything meaningful here. This is like 5 objects. We need hundreds. And there is a new spacecraft that we're expecting to have launched soon called Plato from the European Space Agency that will be staring at 2 more fields, a much larger area, and look at all these young stars it contains. So we're really excited about how many planets we will be able to see around these young stars. And hopefully that'll give us a lot of information about how we get something like our sun and our solar system. So I'll just discuss my conclusions here for a second. So stellar feedback, supernovae, and cloud collisions and galactic structure can initiate and guide star formation. The stellar fossil record provided by young stars provides a history of recent star formation. The combination of simulations with new observations from the Gaia mission can help us reconstruct how star formation happens. And by learning about the environments in which stars can form, that can reveal the conditions that lead to star formation or can lead to the formation of planets like the Earth. So with that, I'll leave it up for questions, and I'd be happy to take them. Thank you. Okay.
Some questions you'd like to?
Yeah, right there. On order, it sort of depends. Oh, yes. How long does it take for stars to form? So it really varies, and it sort of depends on what you consider stars forming to be. So if you start the clock, when the gas is starting to collapse, that could be tens of millions of years. If you're starting at it when you get the triggering event that can cause that rapid collapse, that can be 1 million years. If you're going from when there's a dense core to when the thing forms, that can be 100,000 years. And if you're including the timescale that it takes for the thing to finish that final collapse, that can be another 100 million years. So it really varies a lot depending on what you're considering when you're talking about when stars form. But it's of order 1 to 10 million years. And then some stuff happens very quickly on the 10 to 100,000 a year scale as well. Yes. Yeah. Yes. Mm-hmm. Mm-hmm. Yeah, sure. So they're actually related. So I'll repeat that for a second here. So the first question is, these bubbles. how do they work? It's just sort of like explain that. It was essentially the question. So these bubbles are driven by, you have stars that have just formed, and they produce a lot of light. And that light is so powerful that it can actually push on the gas. And therefore, when you have this star formation, it can expand the gas and produce a cavity where there's no gas, and then around that you get this ridge of gas surrounding that newly formed star. And on the question about like how you get these groupings of stars drifting apart, that's sort of related. If you have a bubble that forms multiple different generations, all of those stars that get formed in the bubble, they're going to have velocities that trace back to the center of the bubble because they're being ejected by the bubble, right? So if you have a bubble, that's a very easy way to get stars moving in these radial directions that when you trace them back, they end up converging. Yep. Yes.
They rotate in one direction, they rotate it.
Yeah. So the speed is more or less dictated by like how much material is like interior to a star in the galaxy. Gas has some other stuff going on because it's subject to interaction with other gas. So gas doesn't quite move at the same speed that stars do necessarily. But what was the other component of your question? Oh, right. Yeah, so we're talking about like what direction galaxies rotate in, and that's really just dictated by like where like, it might be just like a perturbation earlier on in its formation. There's no preferred direction in space, so different galaxies can rotate in different directions. That's just a matter of there's going to be like some direction that has a little bit more stuff going in that direction, and that just ends up becoming the dominant component when you have galaxies form. Way in the back. Yeah. Probably very different. So it's a very different environment, right? So in our local galaxy, we have like a relatively calm environment in which there are young stars that are producing a lot of photons, but it's not nearly as crazy as in the youngest stars, where the first stars that we think existed are like 300 solar masses, these like absolute monster stars, and we think that those were like the dominant form of star formation earlier on in the universe. And you can imagine that if you go from in Cercinus, the most massive thing is like like 20 solar masses, I think. If you go up to 350, that difference in luminosity between a 20 solar mass and a 350 solar mass star, that is not linear. That is like it keeps going. It gets more and more nutty. So yeah, it's an incredibly different environment. From my perspective, like I have this wonderful data from Gaia, which is local observations. I can't get that at a gigaparsec or whatever. So it's just not something that we can do at that distance. So we're going to need like much better telescopes to get to that point.
Time for one last question.
Do you want to pick this one?
Sure, let's go here in the back.
Okay, sure. How are they made? Yeah, sure, of course. So it sort of depends on the simulation what we're talking about here, but I'll just go back to the slides here. So I'll start at large scales and go towards small scales. So when it comes to the largest scales, these are actually zoom-in simulations of like full-on cosmological simulations. So fire actually simulates everything. And all that we do here is we just like take a clump of gas where we know things are dense enough to form stars and let that evolve from, when that overdensity formed out of the cosmic web, this like very early in the formation of structures in the universe. When we get something dense enough to form a galaxy, and then we let that evolve forward, and we get something that looks like this after 12 billion years. Now, when it comes to these simulations here, so the Starford simulations, I'll actually let this play. When it comes to the Starford simulations, this is literally just, you set up a sphere of gas, and then you just, plug in your physics, and then just let it go. right? Just let the thing collapse under your known physics. And when something gets dense enough, then you just like insert a star and then let that star do star things. And this is the sort of result that you get when you just let physics do its course on these sort of spherical cloud. But you don't have to do a spherical cloud. In fact, you probably shouldn't do a spherical cloud. So that's what we're hoping to do with these sort of like simulations of the environment around Circinus. And I've been talking to other simulators about doing some like weirder shapes and trying to like get some different results by looking at different environments.